So my name is Luca Vigano. I'm one of the chairs of POST this year. And I have the pleasure of introducing the invited speaker of POST, Vitaly Shmatikov. Now, Vitaly is a very interesting person, I would say. So when I first started working in security about 15 years ago, one of the first papers that I read is a paper called Constraint Solving for Bounded Process Cryptographic Protocol Analysis, which appeared at CCS 2001. And I thought, well, this is actually a very cool paper, very interesting work. And apparently I was not the only one, because this paper got the Test of Time Award 10 years after at CCS, right? And this is one of the many awards that actually Vitaly has received for his work on security. And what I find particularly interesting about these works is the fact that they cover a wide range of topics. So started in protocol analysis, but then moved to more applied work, moved to work on privacy. In particular, he received twice the Privacy Enhancing Technologies Award. And indeed, today, he will be talking about yet another new field or another area of research that Vitaly has been pioneering for many of us. Vitaly is now professor at Cornell, and he is helping set up the Cornell Tech campus in New York, so the Applied Sciences campus in New York of Cornell. And there he is launching a number of very interesting initiatives, including work on bringing together, or maybe not, depending on the answer to the question, machine learning and privacy. So Vitaly, thanks a lot for being here. We look forward to a very exciting talk.
Thank you so much. Thanks for the introduction. So how do I...
I think just around your...
around my what?
Like...
Sorry.
I think probably like this.
Oh, okay.
Or maybe not.
Maybe not. So.
No?
I seriously don't know.
We need help from... Or maybe...
I have no idea what am I supposed to...
I think it should go around your
complicated
ears.
European thing.
Yes. Yeah, we are getting
Okay,
help.
sorry.
Sorry about this. Which way?
Okay. Oh. Like so. Like this?
Yeah.
Okay, very good.
Thanks a lot.
That feels weird. Okay. Hi. So thanks for the introduction, and thanks for having me here. The work I'm going to be talking about today is very, very new. As a matter of fact, parts of it are not published yet, so you're the first to hear about it. So please bear with me. And most of it was done in collaboration with two postdoctoral fellows, Reza Shokri and Marco Stronati. So credit goes to them as much as to me for the work I'm going to be talking about today. Apparently, there is a revolution going on. And it's a revolution in machine learning. So if you follow the headlines, you are probably aware that there are dramatic advances in machine learning happening all over the place in big companies like Google and Facebook and Microsoft and Baidu. And also there are a lot of academic advances. So big things are happening in machine learning. And this is not an area that I have traditionally worked in, and I knew very little about. So a few years ago, I decided to look a little bit more into this and to try to understand what is it that's going on there and why is it important. And clearly, things that are going on are very big. So I'm sure you've all seen these headlines about dramatic advances in traditional artificial intelligence tasks like speech recognition, image recognition, translation. Google outperforms humans on recognizing cats. Facebook outperforms humans on recognizing dogs. AI is going to own the world very soon. So that's all very interesting and fascinating. And big things are happening. If you do a search for things like deep learning revolution, you find more than several million hits on Google. So the question I'm going to try to investigate today and tell you a little bit about is the question I'm interested in. So I'm not a machine learning researcher. I'm a security and privacy researcher, mostly focusing on privacy these days. So what does this revolution mean for a privacy researcher? So there are all these things happening. So what should we as security and privacy people in my community be thinking about this? And is there a research program here that could lead to interesting research and interesting questions and interesting results? So that's the topic of my talk today. Even a few years ago, when we were looking at privacy issues in my community, we typically looked at the world in which users generate data, transactions, preferences, behavior, web searches, web clicks, mobile app activity, whatever, and then this data is used in various services, web services, online services, apps, and so on. And there are all kinds of interesting privacy questions that we could ask about that. What happens to sensitive personal data when it's being collected? How is it being used? What does it mean for data to be anonymized? How to re-identify anonymous data? What can you infer about people by looking at their online activities and how these activities are used in various services? Are there various side channels through which information leaks out? So this is a very well-explored set of issues that we've been looking at for a number of years. But it looks like the world is changing in a very fundamental way. And it's no longer the case, or soon it will no longer be the case, that most services use user data directly. Now there is machine learning in the middle. And that's in fact the essence of this revolution that's going on, that machine learning, at least it looks like, it's on its way to becoming an essential component of lots of services that we use online, including even not just big things like Google's and Facebook's, but it looks like now even individual apps will have access to machine learning services. So machine learning and models constructed based on user behavior will become part of pretty much anything you do online. And now that you have machine learning in the picture, and now that users' data passes through these machine learning models and is used for training machine learning models before it's being used, that raises a whole set of new issues for us to investigate. For example, if you use machine learning to train a model on users' data, does it actually leak the data on which it is being trained? So that's an interesting question, so I hope to say something interesting about this today. Is it possible to train a good model for whatever notion of good machine learning people use while respecting privacy of the training data? Because as you'll see in a moment, this training data, I mean, it involves people's activities and their transactions and locations. It could be fairly sensitive from a privacy perspective. Another interesting question that I'm not going to talk about today is whether it's possible to learn and keep the model that you constructed actually private, even though it's being used in all kinds of services. That's a pretty fascinating question, but that's not my topic today. But I will try to look at these first two questions. So far I've been talking abstractly about machine learning. Let me make it just a little bit more specific. For the rest of this talk, I will be looking at a very popular class of machine learning models. These are models that do classification. So I'm sure you've all encountered this. For example, every time you do a Google image search, it uses the results of fairly sophisticated machine learning models. So typically in classification, you would run training, supervised or unsupervised, on some training set. For example, in this case, it would be the set of images. And then when the model is trained, you would apply it to an image, and it would classify it. For example, in this case, it would try to identify the type of object that's in this image. And typically in a classification task, it has some number of possible output classes, and it won't just tell you how it classified it. It'll actually give you a vector of confidences or probabilities that tells you how confident the model is that its identification of a particular class is correct. So you can see this. Bars on the right, this is kind of an abstract way of representing probabilities that the model is producing. So in this case, it seems to think that this is an automobile, but there are also other possibilities with lower confidence. So that's how a typical classification model works. It's trained on a whole bunch of data. I'm not telling you just yet how it's trained. That's coming a little later in the talk when it's relevant. But it's trained on a whole bunch of data, and then you can apply it to additional inputs, and it classifies these inputs based on the model that it constructed from the training data. So the interesting thing about this classification is that now fairly powerful technologies for creating these machine learning models are available to anyone. Any app provider, you yourself can actually try it. It's pretty easy to do. And that's the concept of machine learning as a service, which is provided by platforms like Amazon Web Services and Google Cloud Platform is providing it. So this is trying to bring machine learning to the masses and try to encourage anyone who has data that could benefit from machine learning can actually use these platforms to use the power of Google or power of Amazon to train models. And here is how it works. So if you're a data holder, you would take your data, you would upload it through a special API into this cloud service, and then something is going to happen inside. They actually don't tell you a whole lot about what's happening inside, but they're training some kind of model. We don't actually necessarily know what it is, and as a matter of fact, it's adaptive. They decide what kind of model to train based on what they see in the data, and it produces the model. They don't actually give you the model explicitly. Instead, they provide what's known as prediction API. So this is a public API leading to that model that you can use or you can make available to your users whatever you want. So basically, it's a public interface to the model constructed from the training data. Anyone can provide input to it, and then it's going to classify the input based on the model constructed from the training data. So this is the standard way machine learning as a service operates, and this is becoming very big because, like I said, this brings the power of machine learning to anyone who has data in their possession. They don't need to be machine learning experts. They don't need to pay a whole lot of money to expensive consultants. They can just go to Google, Amazon, their favorite cloud platform, and use this service to construct powerful models. But of course, the data that is being used to train these models is potentially sensitive, because these are companies or maybe non-profit organizations, but whoever is using this data, in many cases, the data underlying this model contains some, it's fairly sensitive from a privacy perspective. We're talking transaction preferences, online, offline behavior, whatever is the nature of the data that people are using. So the first question that I'm going to ask in this talk is whether there is any leakage of information from the training data, which is sensitive, that was used to construct the model. Is there any leakage of that information through the public APIs that these services provide for using the model? And it's not obvious. It's not a direct connection there, because this API is not used to access the data. The data is gone at that point. It's just the model constructed from the data. So how would we go about investigating this question? How could we try to exploit the fact that there are these public interfaces to trained models? So as I told you, the way classification works, you provide an input, and it gives you some classification. Suppose I observe the following effect, that in some situations, when I give an input that was part of the training set, as always, it's going to classify it, it's going to give me a vector of confidences. And if I give it an input that's not part of the training set, it's going to produce, again, a classification. So what if, by looking at these classifications, I could recognize the difference between input that was part of the training set and input that was not part of the training set. If I could do that, that would be very useful, and I'll show you in a moment how. If I could do this, that would be pretty good for trying to figure out what was in the training set. Effectively, at the very least, this public API is going to give me an oracle, if you will, for telling with some probability whether a particular input was or was not part of the training set, and that could be a good start for trying to extract information from the model. But how would I do this? How would I recognize this difference? Because part of the problem is I don't actually know what's happening in this cloud. If I knew the particular model they are using, I could maybe try to run it in reverse somehow, do some kind of model inversion, and people have tried to do this, but for this machine learning as a service, I don't even know necessarily what they use. I mean, maybe they're using random forests or decision trees or neural networks. I don't even know the nature of the model inside. So here is where the kind of first insight of this work comes from, is we have this task of telling the difference between something that was part of the training set and something that was not part of the training set. But how would we do this? Well, we actually have a powerful technology at our disposal, a technology that has been rapidly growing in popularity lately and whose power has been increasing. And that technology is called machine learning. So what we're going to do is effectively turn machine learning against itself and train a neural network to recognize when a particular input was or wasn't part of the input data set, of the training data set. So effectively, we use all those advances in deep learning to perform this task. And the beautiful thing about it, it just learns. I actually don't know why it works. Okay, but that's kind of the nature of deep learning. I don't think anybody fully understands why it works. I don't know which features of this confidence vectors it's looking at. But the beautiful thing about it, I don't even need to know what's inside this cloud. All I need to have is enough input-output pairings, and then I just throw a neural network at it and have that neural network learn to recognize with fairly high confidence, as I'll show you the numbers in a moment, when a particular input was or wasn't part of the input data set. And at least in our experiments, the results are pretty good. So the first class of attacks or inferences that I'm going to use it for is membership inference. So this is a very basic application of this power to tell if something was part of the training data set. It's going to work like this. So let's say we have some model of which we don't know specifics, so it's a black box to us. It's a classification model. In this particular case, it classifies images, but you can apply it to any kind of classification task. And let's say I have an image, and I want to know if that image was part of the training data set. So that's the basic membership inference attack. I supply this image to the model. Out comes a vector of confidence values. Then I look at that vector, and from this I tell if this image was part of the training data set. It's not, I mean, in some situations it could be a privacy breach by itself, okay? But that's, for example, if it's a medical data set, then just knowing that somebody's medical record was part of the data set, that's sensitive because the data set is often associated with the condition. But in many cases, it's not really a privacy breach because I already know the data. I'm just learning that it was used in training the model. So by itself, it may not be sensitive, but that's the basic attack that I'm going to use as a building block. In this setting, so I'm going to take a target data record, and using my newly trained neural network, I am going to infer if it was part of the training set. Surprisingly, this actually works pretty well. So these are the results of some experiments that I've never shown to anybody until now. So you're the first people to be looking at this. So this is done on purchase data sets. So we took a data set off of Kaggle of transactions, actual transactions that people did in supermarkets, and set up some classification tasks. And we tried Google's and Amazon's machine learning as a service to train the models. And on many classes, we can predict with pretty high confidence whether a particular purchase was part of the training set or not. So surprisingly, I was pretty amazed when it actually worked, but it did work. So we did manage to train a neural network to recognize it pretty well. But like I said, membership inference by itself might not seem like a big deal. But as often the case in privacy research, once you see a way of inferring a little bit, you just try to bootstrap it and leverage it and build it a little more so you can infer more and more and more. And the next step after membership inference is actually a reconstruction attack, which presents much more serious privacy issues. So again, let's go back to this model, to this idea of machine learning as a service, where you have a trained model, trained on sensitive data like store purchases, or also tried it with location data sets like mobile phone locations and so on. And let's suppose I have a partial record of some user. Maybe I know some of your purchases, a couple, 2, 3, 5, and my goal is to figure out the purchases that are not public, the information that's supposed to remain hidden that you are not telling anyone. So it turns out that if I have a partial record and access to this membership oracle, I can use membership oracle to infer the parts of the record that I don't know. So, and now we have a serious privacy issue here because I turn my ability to test for whether something was part of the training data set into an oracle. You can think of it like we're doing something more complicated than that. We're actually solving some system of equations. But in the simplest case, I can just do it by brute force. I can try all possibilities for the transactions that I don't know about, and then I can submit it to my oracle one by one. And for the one that contains the correct guess of what you purchased, it's going to tell me, yes, that record was part of the training data set. And that's how I will infer the transactions that I don't know about. Now I have a question for you. So why do you think these attacks work? It's like doesn't seem right that they work, okay? There is something not...
Maybe this model is overtrained?
That's exactly the reason they work. Is like if this were a good model, that shouldn't work, right? Because a good model should not be specific to the training input. A good model should not care which sample from the population it's trained on. The fact that these attacks work, the only reason I feel they work is because the model is overfitted to the training data. Well, overfitting is a little hard to avoid, but of course, you know, that's the goal of good machine learning, is to produce models that are not overfitted, because they want models with good predictive power. And here there is something very beautiful going on. And here is why it's beautiful, and here is why this is like a great direction for future research. So let's think kind of what the big picture here is. So we have some data universe, we have some population, and in machine learning, we pick a sample from it, so that's our training set, and we construct a model. As privacy people, we care about the following question. Does the model leak information about the training set? That's effectively the attack I've just shown you now. I've shown you that the model does leak information about, in many cases, models constructed using this machine learning as a service do leak a lot of information about the training set. That's the privacy question. What do you think machine learning people care about when they construct models? They typically don't care about privacy. They care about creating good models. What do you think a good model means to a machine learning person? High predictive power, absolutely. That's pretty much the only thing you care about as a machine learning person. So what do you want a model? High predictive power. But technically, what does this mean? This means that the model generalizes to data outside the training set. Meaning that if you took a different sample, you would get pretty much the same model. What do you think about these two questions? It's the same question. in some sense, overfitting is the common enemy. So what you want to have privacy is exactly what you want as a machine learning expert when you want to get a model with high predictive power. And the reason this is so exciting to me as a privacy researcher is that typically when you do privacy research, which I've been trying to do with very intermittent success for 10 years or so, you have this trade-off between privacy and utility, okay? You can get either a lot of utility but not a whole lot of privacy, or you get a lot of privacy but the computation or the data is not very useful. So you're always living on this curve, and you always have to argue with people, well, you have to sacrifice utility to get privacy. But in this case, in the case of machine learning, it seems as if there is no trade-off. As if with, like, you can get machine learning that's privacy preserving and has high predictive power. So you do not have to sacrifice privacy. All you need to do is to construct a good model and it'll be privacy preserving automatically, and vice versa. Well, it's not quite like that. I'm not making a precise statement, but the nice thing here is that all of a sudden we're on the same page. I don't have to argue with people about how to construct, why it's important for them to have privacy and why they need to sacrifice utility. So overfitting here is the common enemy. This is what causes privacy violations, and this is what causes this is what leads to bad quality models that don't have predictive power. So now let me talk a little bit about how to do this, how to do privacy-preserving learning, and how to construct models that are good and that are privacy-preserving and have predictive power that are good from the machine learning perspective. So but first I need to give you like a very short, like 5-minute, 10-minute introduction to how learning works today, because this is going to be important when I describe the details of our privacy-preserving learning system. So the way learning works today is fairly centralized. The reason for this is that deep learning is what everybody uses these days, and it really seems to benefit from large volumes of training data. So every time you take your cell phone and you speak something into it and it recognizes your command, whatever you spoke into it gets uploaded, depending on the phone you use, to Apple servers or Google servers, and they run massive machine learning on it. So this is centralized learning. What I'd like to replace it with is some kind of privacy-preserving protocol that achieves the same thing but in a distributed setting where there is no central party that gets data from every participant. And I'll explain to you in a moment why this is a meaningful objection, why it's actually important for many people, and it's not just my fantasy as a privacy person, it's actually essential for a lot of people who have sensitive data. But first, let's talk a little bit about how this learning works. I keep referring to these deep neural networks. That's a very popular learning method today. I'm sure many of you have heard about it, but I'm going to give you like a really short tutorial, and please bear with me. I'm not a neural network expert at all, so this is just stuff I learned while doing this research. So please bear with me if I say something that's wrong, or I'm just a beginner in this. Oh. Okay. So the goal here, again, I'll be working in this classification setting, but it easily generalizes to other settings. So a neural network would take some input and pass it through many layers. That's why it's called deep learning, because modern networks have hundreds of layers. And at each level of the network, the features being recognized become more abstract, if you will. So the initial layers are going to recognize low-level features, and then gradually, in this case, the task is face recognition, so output is going to correspond to actual faces. At each level of the neural network, this is actually fairly simple animals computationally. So at each level, we have so-called neurons, which send their signals to the activation function, and each neuron contributes with a certain weight. So these are the parameters of the training. Then the activation function is applied, and different activation functions are used in the literature. It's not so important for the purposes of this talk. And it could be a step function or some kind of sigmoid function. And then the output feeds to the next layer. So in effect, the goal of neural network training, what happens when these models are being trained, is finding the right set of parameters. And modern neural networks, they have millions of parameters, so it's a huge number of possibilities. And during training, so this is what happens inside Google on this massive GPU clusters that they have for doing this, is learning parameters of the neural networks. There is a constant learning process going on, and it's an optimization problem, and they solve it using something called stochastic gradient descent, which is a very standard technique applied to this neural network setting. So here is how it works, this finding parameters using stochastic gradient descent. So we have this massive network. We have weights on every connection inside the network. And again, it could be a fully connected network or a partially connected network. Not so important. What's important here is that there are all these parameters on interconnections. And the goal of the training is to find the parameters that minimize the classification error. So you start with some input, and in the first step of the training, you just push it forward through the network. So you apply all these individual neurons and activation functions with appropriate weights, and it's going to produce some output. And this output might be good or not so good, so you calculate the error between what it produced and what you wanted to produce. So in this case, I'm dealing with supervised training, but unsupervised is very similar. And now, once you have the error, your goal is to find the weights of the parameters that would minimize that error. And the way you do this is by backpropagation. So you take this error, and you sort of send it back along the connections. And at each step of this backpropagation, what you try to do is to adjust individual weights so as to minimize this error. So that's all you're doing at every step. So this is the standard gradient descent algorithm from like a textbook or Wikipedia. So that's all that's really going on here, trying to minimize the value of these weights. And you keep doing this. So you keep submitting it batches of training data. You feed it forward, you calculate there, you feed it back, you adjust weights. Another batch of training data. You do this again. Feed forward, backpropagate, adjust weights. And you go through huge amounts of training data and huge and lots of rounds of this adjustment and so on. And you end up with models that perform very well. You could ask all kinds of questions like, why does this converge? I don't actually think anybody really knows, and sometimes it doesn't converge. There are all kinds of tricks and tweaks and various cleverness that these companies use to make it work, but empirically it does. It just does, okay? That's why we have all this amazing translation and speech and image recognition and all these beautiful machine learning services today, and why we're reading these headlines about dramatic advances. So it works. So that's how. This is just textbook neural network training. That's what they do. But remember, they do it on a centralized training pool. So data from everybody comes into this big pool of training data, and then this process keeps running and running on this data, on these data sets containing millions of data samples from millions of people. The important part for me, when I get to the privacy part of it, will be parameter updates. So this is what you need to take from that story, is that during this training, there is a constant process of adjusting parameters. So some parameters go up, some parameters go down as the training progresses. But in this centralized setting, so we're dealing with sensitive training data. Users typically have no control over the training objective, meaning that you just send your data to some service. You have no idea what they're actually learning. They could be learning things that are actually harmful to you, or that try to infer things from the data that you don't want inferred. So even using this network, they're not giving you the model. They're giving you API access to the model. So just to use the model, you have to give them the data. Even if after the model has been trained, to take advantage of it, you need to send them the data, then the cloud sends you back the output. It's useful, but again, training it requires users to share data, and using it requires users to share data. And there are all kinds of risks. Data could be used in the wrong context. All these services end up storing massive amounts of user data, and who knows what happens to it. I'm told they're routinely compromised in various ways. There are like 3-letter government agencies spying on them. Who knows what's happening there? That's the privacy concern. But what's even more important is because of this way of doing training, there are many people who would like to take advantage of it, but they can't because they're not allowed to share data. Probably the most prominent example of this is biomedical research. In many cases, people who hold biomedical data, images, tissue samples, clinical histories, what have you, they're not allowed to share it with anybody. And this is the kind of data, for example, if we're talking about personalized predictive medicine and finding correlations between disease and genetic features, that's something that could really, really benefit from large-scale training, from large-scale machine learning and training powerful models. And today they cannot benefit from this at all because they cannot share the data. They effectively have to train on their individual data sets, and the power of this learning, it comes from having a big, massive data set. So in this case, it's not just a privacy concern, it's also a utility concern, meaning that there is this powerful technology out there, deep learning, and people who have data that could really benefit from deep learning cannot take advantage of deep learning because they're not allowed to share their training data sets. So that's the problem that I would like to solve. So effectively, by solving the privacy problem, I will also help them solve the utility problem. So just to summarize, what I'm trying to do here is that's the situation we have today, where we have a whole bunch of sensitive data and feed it into some model. And today, the sensitive data effectively has to be shared with someone. I'd like to do the same thing, but keep it private. And the model today is private to whoever collected this data and trained the model. And I want to flip it and make the model public so that everybody can benefit from it. But other than that, I want to train neural networks that have the same predictive power as what would be achieved with centralized training. So that's my objective here. So I want to run this training that I described, but without a centralized party, but by using some kind of protocol with minimal information exchange between participants. And this is the protocol that we developed that we call Distributed Selective Stochastic Gradient Descent, DSSGD, which tries to run standard neural network training, but in a distributed setting where multiple participants do not have to share and do not have to pool their training data. So here is how selective stochastic gradient descent works. The parties train concurrently and independently. So in this case, the participant just runs the training on their own data set. And as they run the training, they're going to be adjusting parameters based on their local training. And all we ask them to do is when they see substantial parameter changes, just inform other participants which parameters have changed during training and how. So they don't have to share all parameters, they have to share just a few, but the important ones, so that this parameter went up a lot and that parameter went down by a lot. And same thing, so everybody training, they look at their important parameters and then they share these parameters with other participants. So the intuition here is that somehow the important information about my training data set, what's important for the model, is captured by these parameter changes. So maybe I can achieve the effect of centralized training not by sharing the training data, but by sharing what's important about this training data. And this is captured by these changes in the parameters that happen as I'm training. And as I'll show you in a moment, I don't even have to share like a whole lot. I can just share a little bit. So, and we set up a system and developed a protocol that allows people to do this. So roughly it works like I described. So every participant trains independently on their own data set, but then they select a few gradients in the important parameters, and they upload them to a centralized server. And then everybody can download parameters from that server. So that server acts as a common bulletin board on which people training concurrently can post information about parameters as they change during their training. And not all parameters, just the important one. They can say, this parameter went up a lot on this batch, and that parameter went down a lot on this batch. Then they go to the next batch, and they share this information. And then this information about parameter updates is incorporated by everybody into their own training, and this way, it kind of has the same effect as if they were like swapping information about their models, but instead of swapping information about the models, during training, they just swap information about what are the important things that happened as models were being trained. And because of the way this protocol is designed, sooner or later they end up converging to the same model because they're exchanging information about big parameter changes, so they end up with the same set of parameters and they converge to the model. So this protocol has very nice features. Training is local. It doesn't require sharing of the training data set, but it does, because of this parameter sharing, it does result in global convergence most of the time. So it does converge to a single global model. Because of this parameter updates, these are not reliable updates. Many of them could get lost, one could override the other, but that's actually not a problem. If anything, it introduces stochasticity into the training process, and for neural networks, stochasticity is good because it prevents overfitting. The big risk, as I showed you in the first part of this talk, if I'm training a model on my own data set, I may very easily end up overfitting to my training data. But my training is constantly disturbed by parameter updates from other people, and those parameter updates have nothing to do with my data. They're not even seeing my data. So that introduces stochasticity into my training that prevents me from overfitting. So we end up with a global model that's not overfitted to any individual batch of data, any individual training data set, because parameters came from everybody. Let me show you some results. So these are for recognizing handwritten digits, which is a very standard classification task that is often used for benchmarking machine learning algorithms. So, okay, so here is what this chart shows. So this line at the top, this is centralized training. This is no privacy. This is the gold standard for me. This is what happens if you take all the training data, pull it together, and learn a model. Okay? That's what we want to achieve. This is the accuracy of the model that you would achieve in standalone training. So if you trained on your own data, that's what you would get. You can see there is a big gap between them. That's why pooling the data is so important. That's exactly what I keep saying, that these models benefit from having a lot of training data because that gives you this jump from the lower line to the upper line. And these curves, they show collaborative training. And you can see that by doing this parameter exchange, you get models that are almost as good as what you would get by pooling training data, even though these do not involve any data sharing. And you get these models that are good. So this is the most important number here, this one here. So this just says that if I share only 1% of my parameters, 1 out of 100, so there is very, very little sharing going on. I'm not sharing my training data. I'm not sharing 99% of my parameters. Just 1% of my parameters I'm sharing with other participants as I'm training. If I do this, if we all do this in collaborative training, we're going to end up with a model that's almost as good as if we took all of our training data sets, pooled them together into one big training data set, and trained on it. So that, to me, is a pretty amazing result. It's like how little sharing is required to get the effect of centralized training. So that's nice. I feel that's nice. Okay. So what do you get by doing this? Participant data sets remain private. They have full control over which parameters to share. They can share important parameters. They can even share parameters chosen randomly. It actually still works pretty well, just convergence takes longer. They fully control what their learning objective is, so there is no longer a risk that I share the data and somebody learns something from it that's different from what I want them to learn. And they come up with a public model. So the model is no longer hidden in a black box behind an API. All participants in this process learn the same model, and they know what the model is. They know the set of parameters. So that's good. There is one little twist here that might be a little annoying. They do some sharing. So they do share these updates to parameters, these gradients. So there is a risk that information could be leaked through those updates. I actually don't know how much information is leaked, and it's not obvious how to infer anything useful from these updates, but it is a risk. So there is a concern that maybe one of the participants is malicious. They're looking at parameter updates that are coming to them, and they say, oh, maybe I can figure out, maybe they can do a membership inference attack, like I described before. So that's a risk. So to mitigate this risk, we have to do something. We have to try to modify the parameter update protocol, the parameter exchange protocol, to hide the fact that somebody's data is in the training data set. And we use it using fairly standard techniques from differential privacy. So instead of using this parameter selection and gradient sharing that I've just described, we have a differentially private version of it. So the values that we exchange, they're perturbed in a differentially private way. So this is a fairly standard application of differential privacy, so I don't have a whole lot of interesting to say about it. So this is pretty much textbook differential privacy. It does require one technical trick here. We need to use something known as the sparse vector technique, because we're only sharing a small fraction of parameters, and if we do it naively, that is, if we add noise to all parameters, we're very quickly going to run out of the privacy budget, such as it is. So what we do instead, we use this sparse vector technique that allows us to do a differentially private comparison between the values and the threshold, and we end up sharing a small fraction of parameter updates that are above the threshold. So it works pretty well. So this is a chart that shows the results of differentially private training. It's not as accurate if we don't use differential privacy, but it does result still in fairly accurate models that take a little longer to converge. So, what am I trying to say here? So, I feel that machine learning is about to become pervasive in all kinds of internet services. And that's both a threat and an opportunity, especially for privacy researchers like myself. There is a whole class of new risks to data that come from the use of machine learning services, especially if they are not used carefully. If you end up with models that are overfitted or use machine learning improperly, you're going to introduce new risks to personal data that we didn't have before. But at the same time, it's a huge opportunity. And this is the part that I'm really excited about, is that all of a sudden, privacy and utility no longer seem to be in conflict. Overfitting is the common enemy, because overfitted models leak sensitive data, and they also lack predictive power. So we're on the same page here. This is good. This means that it is possible to design privacy-preserving machine learning systems. And the system I described, this is just the first step. There are many ways in which it could be improved. There are many other learning algorithms, learning scenarios. So like I said, this is just the first step on a long road. But there is opportunity to design systems here that let you have your cake and eat it too, that are going to produce high-quality models, but do not require participants to disclose their training data. They will let them fully control the learning process, fully control its objectives, and so on. So you can get as much privacy as you want, and at the same time come up with models that have high predictive power. And that's what I hope will happen. I hope that I feel it has to happen, because like I said, there are many participants now who have data sets who cannot take advantage of machine learning today because they're not allowed to share the data by security reasons, regulatory reasons, and so on. So by helping them get the benefit without sharing the data, I feel this could really make the world a better place. And I think I'll finish here, and I'm happy to take a few questions. Thanks.
Let me try and find at least. Yes, we do have time for a number of questions. There was one there in the back. If you can wait for the mic. Thanks.
Thanks for the nice talk. I learned a lot in less than an hour. But the end result, I find, has a paradox, because you start with centralized learning. Then you did this privacy attack to get information from the model. And now you have a distributed version that learns slightly less, very good, but slightly less than the central one. And according to the hypothesis, this should then also leak more information, right? So did you try again the privacy attacks on the distributed model? And shouldn't you get, shouldn't it leak more information since all the parameters just encode the original information?
That's a good question. So it's not that, okay, so the parameters don't quite encode original information. So the parameters, they abstract enough from the original information that at least the attacks that I described in the beginning, they do not work against models trained using these techniques. But I don't want to make an absolute statement here. To be honest, this work is in very early stages. This is all like black art and magic, and we don't fully understand why things work or not. But the hope is here to come up with a way of training that produces parameters that are not specific to the training data set. So they capture something that is true about the entire population, but not necessarily true about the sample on which the model was trained. And if that is the case, if we achieve this, then it shouldn't be possible to infer from the parameters information about a specific sample, because if we use the different sample, we would have come up with the same parameters. Sorry, it's hard for me to make a precise statement.
Okay, I'm a bit, I have a different opinion of privacy. If you have a perfect model and you can really totally predict everybody correctly, okay, this in your sense would be totally privacy preserving. On the other hand side, you put the glass person in the world, which you can predict. So in this sense, it is not privacy preserving. You know what I mean? So you cannot predict the training set, fine, but on the other hand side, every person is just open late to you. So is this not also a kind of threat?
You're right. I mean, I'm using a very specific notion of privacy here, which is whatever the model is producing has to be true about the entire population and not true about the specific training set. The general problem that you're describing, how do I make sure that the model doesn't allow inference of a certain kind of information about a person? I don't know how to solve that problem. That is a very, very hard problem. It's known as inference control. It's just diabolically hard. I've thought about it for a while, and I don't even know where to start handling it. Sorry, that honest answer here.
Thank you very much. Great talk. Highly interesting, Vitaly.
I'm sorry, I don't. Oh, there you are. Okay. Sorry.
Hi. So maybe a follow-up question on this. So I was not entirely convinced about the fact that in this case you don't have actually a trade-off between privacy and utility, because it seems to me that actually as long as the model is predictive, meaning as long as actually my data somehow contributes to the model, then actually my data influences the model, and this is the typical reasoning, for instance, in differential privacy or for impossibility results in the literature. So it seems to me that as long as my data are useful for the creation of the model, then actually my participation in the model is leaked somehow by, well, the effect of the machine learning procedure. So what's your take on that?
So maybe differential privacy is an analogy that you might appreciate. So the notion of privacy that we're getting here, it's not quite differential privacy, but it's similar to differential privacy in spirit, which is of course, some information is leaked because things about you are being learned. But the idea is that same things would have been learned even if you weren't part of the training set. And that's about as strong a guarantee as you can realistically hope to give someone. So the sentence that I just said, I mean, that's the standard motivation for differential privacy. And we're after something similar here, is the utility of the model comes from the fact that it's capturing facts that are true about the population, okay? That are not true about you individually, but that are true about the population. And of course, you contribute to them because you're part of the population, so you influence what is being learned, of course. But the hope is that it's becoming harder to learn things that are unique about you. It's only the features of you that you share with the population that are being learned, and not something that is individual to you. So that's the subtle notion of privacy that I'm after here, if that makes sense.
So there was somebody there, exactly, then two people there, and then one here in front again.
Oh, boy.
Thanks. So the question is, could you maybe revisit the convergence issue that we slightly touched? Because my intuition runs completely opposite to what you said. If you have a procedure to accomplish some task, and I have a procedure to accomplish the same task, and if we kind of exchange parts or parameters of these procedures, my intuition would be that the whole thing will completely break.
Yeah, like, exactly. Like, you're converging, and meanwhile, I'll tell you, no, your parameters go that way. And you're like, okay. So, all I can tell you, I have no, like, rigorous result about convergence. None, okay? All I can tell you is that, empirically, it seems to converge. Why? Because it happens that if your data is a little different from mine, you train on a batch, and you're affecting like this set of parameters. And my batch is different, and I'm affecting this set of parameters, and the two don't clash. Occasionally, we do see situations when, like, I did an update, and you just overrode my update, and we just, But somehow, like, this training seems to benefit from some diversity in the training data set. As you see what I'm saying is that because our sets are slightly different, we're adjusting different sets of parameters. And effectively, in the resulting model, it looks as if it's not really like that. But in each update, it's as if like half the parameters came from you and half came from me. And these are almost different halves. The overlap is small. And because of that, we converge. But this is like total hand-waving. This is just empirically what we observed when we run these experiments. But like, I'm as surprised as you. I have no idea why it converges. It just does in our experiments. Yeah.
Okay. I wonder what Amazon, Google, and co. think about your work. Do they like it, or do they rather want all the data without us thinking about it?
Yeah, what do they think? What do I care what they think, right? Are you asking about the distributed learning work or the inference attacks?
I don't have a microphone anymore. I was thinking about the privacy issue as a whole.
Okay. Okay, good. So let me give you a long answer because that's an important question. Privacy issue, I don't know if they genuinely care about privacy, okay? I mean, their goal is to collect data from everybody and train powerful models. Yeah, but you don't. I mean, maybe not you personally, but you collectively as a population. That said, some of these techniques help people use their services in situations when they're not allowed to share the data. That is definitely helpful because they want people to use their services. This distributed learning has applications even without privacy concerns. Like if you have, because it allows you to take advantage of things that are very weakly, that are concurrent but have very weak interconnections because it minimizes the exchange for parallel training. And I do see papers coming out of Google now that actually cite our work as part of their inspiration for how to do distributed learning without any privacy concerns at all. And as far as inference attacks are concerned, well, I told you in the beginning, you are the first audience I'm talking to about this. I meant it. You're the first people, and that includes Google and Amazon, or excludes them rather, who hear about this. So we have not yet talked to them about this.
So there is time for one final question here in the front.
Thank you. I think a fundamental problem behind this learning and your differential privacy notion is that we should have a sample that is a good representative for the whole data set. If you find such a sample, then it will be difficult to infer information about what was in the training set or not. If you have a bad sample that only shows, for example, red automobiles, then it will be much more easy to infer.
That is true. That is true. That is absolutely true. With one little caveat. Even if you had a good sample, you can still overfit. Because there is always something in the sample that's unique to that sample. Like if you're learning something that is really specific, the sample statistically could be a very good representative of the population. But you could still manage to overfit even to a good sample. But you're right. I mean, that's, I feel, part of the reason why this learning benefits so much from having a lot of training data is because effectively it creates really representative samples and very big ones and so on. But then the important thing is that you really have to be learning the features that they have in common. But of course, if you have a really big sample, it's sufficiently diverse that if you end up learning, it is the features that characterize the entire data set, not the sample. And look, I mean, honestly, I'm not a machine learning researcher. I'm not a statistician. I'm just a privacy guy who sees an interesting problem and tries to, I just try to grope my way to something. So I think the question you ask is really a fundamental question about machine learning. And it's a very important one, yeah.
So Vitaly, judging from the hands that were still raised, I think you will have a very busy coffee break. Okay. But this also means that your talk was extremely inspiring and thought-provoking, and I would like to thank you for that. And here is a small token of appreciation from ETAPS.
Thank you. All right.
Thanks a lot.
Thank you so much.